to walk a dog or something like that. I mean, it's probably for the better, and that it gets you going earlier. But anyways, yeah. So we're gonna continue doing this stuff. Whatever I cover today, like wherever I end, that's like the last thing that will be covered for the exam next week. I don't know if you've seen this or not. Some of you have, some of you probably haven't. But I did move back the homework to next week, so that way it's due on Tuesday. I said I was going to do it in class last week, and I did that. Um, that said, I will be posting an exam review, and I don't know. Like, I think it would be good to get the homework done this week, so that way you can just focus on the exam review next week. But and you have the freedom to choose your own path. I suppose. If you want to do the homework next week and then do the exam review on like Wednesday, Thursday, that is a possibility as well. Does anyone need the notes I handed out yesterday or on Monday at all? Yeah, so I'll probably do like one more example involving diagonalizing matrices, and then I'll go into symmetric matrices. And so I think there's a couple more proofs I wanted to go through. I'm not going to do there's like a problem involving Fibonacci numbers on the fourth page. I might make that a homework problem, due, I guess, in like 2 weeks or something, or however long it's going to be. But yeah, we were talking about diagonalization. This is one of the main applications of looking at eigenvalues and eigenvectors. It effectively gives you a way of thinking about certain matrices as diagonal matrices. And diagonal matrices are kind of like numbers in the sense that we're going to see later diagonal matrices are commutative. You can multiply diagonal matrices in whatever order you want. It's easy to take powers of diagonal matrices. Uh, it's easy to take determinants, traces, whatever you want for diagonal matrices that are the nicest possible matrices to work with. So if we can take a matrix and say they're effectively diagonal matrices, they must be really nice matrices, is what I'm getting at. And so what we found, this is the main takeaway from Monday's class, is that if we have a matrix A that has n linearly independent eigenvectors with eigenvalues given by lambda 1 to lambda n, then that means that you're going to be able to express A as the following product. So this is kind of like it's called a conjugation. So this is like the conjugate. You don't need to know that terminology, but you have x times lambda times x inverse, where x is a matrix whose column vectors are given by your linearly independent eigenvectors. And then lambda is a diagonal matrix where the diagonal is just your eigenvalues. And so if you can find eigenvalues and eigenvectors and you see the eigenvectors are independent, then it's not so bad to find the diagonalization. And so we found a couple of other properties, like this idea of diagonalization plays into this larger idea of similarity, where we say two matrices are similar if A can be expressed as P times B times P inverse, where P is invertible. So these similar matrices, it preserves determinants, ranks, eigenvalues, and traces. So we showed that if two matrices are similar, they have the same determinant. So in the diagonalization case, we're saying the determinant of A is the same as the determinant of this lambda. Okay, question. Yeah. Oh yeah, I asked in the beginning of class. But yeah, you can come over. Oh yeah, I can pass it back. That's another idea. But you showed the determinants are the same if they're similar. And then another major application of this diagonalization idea is it allows us to find powers of matrices in a way that's like 100 times easier, in the sense that it's like if you had the choice between doing a to the 100th power, i.e. multiplying the same matrix to itself 100 times, or if you had the choice of taking 100th power of just a real number, you're going to want to go with finding the power of the real number and then performing some matrix multiplication. So this is like multiplying matrices 100 times with itself. This is just doing the matrix product of three matrices, which like the number of operations you're performing is significantly less. Okay, and so we did one example where this is where we concluded, right? We looked at a to the fifth power, where A was the following matrix. We found the eigenvalues and eigenvectors of A in the previous problem. So from there, we were able to diagonalize A using x, lambda, and x inverse in the following way. A to the fifth power then just becomes x times x inverse to the fifth power. And the main thing is that this fifth power is just applied to lambda, where lambda is this diagonal matrix. So you just take each entry of lambda and then you just raise it to the fifth power. So it works exactly as you would expect it to. There isn't any sort of additional complication that arises. And so we're going to do this example, and then we'll probably just go on to 6.4. And so these are other nice results that follow from diagonalization and similarity. So the first thing tells us that if we have a matrix X that diagonalizes both A and B, then we end up having that A times B is equal to B times A. So in general, the order matters for matrix multiplication. It doesn't commute, but it turns out if they have the same matrix X that diagonalizes them, then it actually doesn't matter the order in which you multiply them. And so how we're going to begin this is we're just going to suppose that we have that A is equal to X times some lambda 1, and then you have X inverse. And then we have B. So we're saying that A and B are diagonalized by X. So we're going to keep X the exact same. So this is going to be X. The only thing that's going to be different is going to be the lambda 2, or like the diagonal matrix, which I'm going to denote as lambda 2. And so if we multiply these two matrices together, you kind of see what happens, right? You're going to have X inverse times X, which will cancel out. So you get A times B. This will be equal to X times lambda 1, X inverse. And then you times B. That's going to be X times lambda 2 times X inverse. And so I'm just going to get rid of these parentheses here. Write them like so. And what happens is you have X inverse times X. They cancel out with one another. This ends up giving you X times lambda 1 times lambda 2 times X inverse. So these are diagonal matrices. I'm going to show what happens in the 2 by 2 case. But the main thing is these matrices are going to be able to compute with one another. Again, it's what I've been saying before, in that when you're doing these diagonal matrices, it's pretty much like you're working with real numbers, except you just have a collection of them. In the sense that if I did something like A, 0, 0, B, and I multiplied it to a matrix of the form C, 0, 0, D, if I were to multiply these matrices, it's just going to be equal to A times C, and then you get 0, 0, B times D. And then you can flip the order of the multiplication here. And this would be the same as just doing C 0, 0, D times A 0, 0, B, right? Because then you'll get C times A, which is the same as A times C, because these are just real numbers. You would have the dot product of this with this would just be 0. This would be 0. And then you get B times B here. So this is just demonstrating that when you have diagonal matrices, it doesn't matter the order in which you multiply them, right? Because it's effectively just real multiplication along the diagonal. So maybe you probably don't have to write this down, or if you want to write down what's going on, you can. But the main idea is you can flip the order of this multiplication. So that way, this is going to be equal to X, and then you have lambda 2, lambda 1, and then you have X inverse. So there's kind of one more step here. We want to be able to say that we started with AB and we want to finish with B times A. Does anyone see what do I have to do to this to make it so I end up getting B times A without actually changing the actual value of what this matrix is going to be?
All right, go. You could throw an X and an X inverse in there in between the lambdas.
Yeah, so this is kind of a common trick, is I can just kind of undo this canceling I did before. So this is the same thing as doing X times lambda 2. And then in between lambda 2 and lambda 1, I'm going to have X inverse times X. And then this will be lambda 1, and this will be X inverse. And so now this part here, this is our B. This part here, this is our A. Right? Just using how we defined A and B in the beginning. And so this ends up being equal to B times A. Right, so we're making use of the fact that diagonal matrices, and again, this is only for diagonal matrices where you can make this assumption, but for diagonal matrices, you can switch the order of multiplication from this principle here. Technically, you would want to show it for like n by n matrices, but and the intuition, it's is demonstrated in the 2x2 example. Okay, any questions about part 1? Yeah, part 2, this is going beyond just talking about diagonalization and talking about similarity in general. So we're saying that, so the claim here for 2 is we're saying that if A and B are similar, then they have the same eigenvalues. This isn't making any sort of statement about the eigenvectors. The eigenvectors could be different, but we're just saying they have the same eigenvalues. And so how I'm going to begin this is I'm going to suppose that we have that AX is equal to lambda X. So we're saying that A has an eigenvalue given by lambda and an eigenvector given by X. And we're saying that A and B are similar to one another. So when I'm saying that A and B are similar to one another, what this immediately translates to and how you should be thinking about this is just saying that A is equal to P times B times P inverse. That's just the definition of what it means for two matrices to be similar. And so what this means is the following. So we want to make use of that fact. And so I'm going to take this AX. In one direction, we know that this is equal to lambda X. And then using the fact that A is similar to B, we can substitute in A is equal to P times B times P inverse. So this is going to be P times B times P inverse times X. Let me write the -1 power a little bit more clearly. Right, so that's just substitution, right? From the fact that A and B are similar, we get this equality. And then what we want to do is we want to show that B is also going to have an eigenvector or an eigenvalue of lambda, right? So we want to take this B and we want to get a lambda to show up somewhere. Or I don't know, that's maybe not the best way of wording it, but we kind of already are involving B with lambda in some way. But we want to think about like B multiplied by some matrix is going to be equal to something involving lambda. That's kind of what I'm getting. Maybe it's kind of hard to like summarize it simply in words, but does anyone see what I can do? Like, so we have these two equations, and we want to say that B has eigenvalue lambda. Does anyone have an idea on what we do? Really to these two equations that we have here, like this equality. And I'll say it's kind of one step. You just want to perform a matrix multiplication. Does anyone see what you want to multiply by? Maybe it's a little. So I kind of like how I'm thinking about things is I kind of want B to be the leftmost matrix here, which means I want to get rid of this P here. And maybe it's kind of hard to see why I want B to be the leftmost matrix, but what I'm going to do is I'm going to multiply both sides by P inverse. Again, by the definition of similarity, we're assuming that P is an invertible matrix. So we can multiply both sides by P inverse. And I mean, we have P inverse already. So if you multiply both sides by P inverse, that's going to give you B. And then you have P inverse times X. And then we're multiplying this matrix, or really this vector, by P inverse as well. So this is going to be equal to P inverse. And then you have lambda X. And the main idea now is we can take this lambda. This is just a constant value. So you can move constants wherever you want in these matrix formulas. So I'm going to move it in front of P inverse. And in doing so, we're going to get B times P inverse times X is equal to lambda times P inverse times X. And then what does this mean, I guess? So this is like all the work that you have to do, but then maybe you have to have like one line at the end. Like, what is this saying? Does anyone see like how to articulate this? Like, what's that?
Therefore, B is equal to lambda.
B is not going to be equal to lambda. Like you should be thinking, like B is a matrix and lambda is just like it's just like a real number. Like you're just saying, like when we multiply B to this vector that we have here. It ends up being equal to lambda times this vector. What does that mean? In other words? Yeah, Mason.
Times x is an eigen.
Yeah, exactly. So like what's going on here, and this is maybe like a better way of writing it, but I didn't want to, this kind of maybe gives the answer away. But like what's going on is if we do b times p inverse times x, it's the same thing as lambda times p inverse times x. And so p inverse times x, when you're doing a matrix times a vector, is just equal to a vector. Maybe it takes some getting used to, but this is just a vector. This is just a vector. And we're saying if we do b times this vector, it's equal to lambda times this vector. So in other words, lambda is an eigenvalue for b with eigenvector given by p inverse times x. So just writing exactly what I just said. So by definition, we can say something like this. P inverse times x is an eigenvector of b. But the main point is that the eigenvalue hasn't changed at all. So the eigenvalue is lambda with eigenvalue lambda, right? So what I'm saying is that if lambda is an eigenvalue of a, we have that lambda is still an eigenvalue of b. I didn't say anything about the eigenvectors though, right? Like the eigenvector ended up changing. We went from x to p inverse times x. So the eigenvector is changing, but the eigenvalue is still lambda. So the eigenvalues are preserved, but the eigenvectors could change whenever you have two similar matrices. Any questions about this one? Problem 2. Yeah, you can kind of see like when we're in chapter 6 and onwards, it's kind of becoming a little bit more proof based. Like we're focusing a lot more on doing proofs rather than like the computations we were doing before, which is kind of it's gonna be the trend in this class a little bit. This next example, it's a good one, but I don't think I'm gonna do it. It takes a long time to get through, but it's not so bad. Maybe I'll give you like the gist of it before moving on to the next section. Maybe until like I can talk about it until like 12:25, and then the other half of class will be on 6.4 or something. So the main point of this, like I've been talking about, like how using powers of matrices could be helpful for solving certain kinds of problems, and we know how to find powers of matrices now via diagonalization, via like eigenvectors and eigenvalues. And so using diagonalization, we can find any Fibonacci number that we want. So you can find like the 1000th Fibonacci number just by doing a matrix product. And there ends up being like a pretty nice formula for this that we can derive. So just as a reminder, the Fibonacci numbers, it's a sequence of numbers that are defined recursively as like if you're doing the k plus 2 Fibonacci number, it ends up just being equal to the sum of the two previous terms. So if you wanted to find what the third Fibonacci number would be, it would be the second plus the first. And then you're given the initial conditions where you have the 0th Fibonacci number is 0, and then the first is equal to 1. And so we're going to define a vector u sub k, where the first component is the k plus 1 Fibonacci number, and then the second component is the kth Fibonacci number. So if you understand this vector, it means you understand what the kth Fibonacci number is going to be. And then if you added these two components together, it'll give you the k plus 2 Fibonacci number. And so there's a way of thinking about Fibonacci numbers in terms of matrix products. So for example, if I did this matrix 1, 1, 1, 0 here, and I multiplied it to this u sub k vector, it would look something like the following. So you would have 1, 1, 1, 0, and then this is going to be f of k plus 1, f of k. If I perform this matrix product, the first term is going to be f of k plus 1, and then you have f of k. Sorry, it should have been a plus sign. So plus f of k. And then the second component is just going to be f of k plus 1 plus 0. So it's going to be f of k plus 1. If I wanted to express this vector in terms of u, like what is this vector going to be equal to? Does anyone see? Yeah, you should be thinking this first one, like we have f of k plus 1 plus f of k. It's going to be f of k plus 2. So we can rewrite this as being equal to f of k plus 2. And then we have f of k plus 1. And so that's just equal to uk plus 1, right? So this is equal to u sub k plus 1. Right, so what I'm getting at is if we take this matrix 1, 1, 1, 0, and you multiply it by uk, it's going to make it so the index increases by 1. And so it makes sense that if we consider powers of this matrix, it's going to allow us to increment whatever this vector is going to be by an arbitrary amount, pretty much. And so the main idea is this. So this is an idea that you could go into more detail about, but I'm just going to give you the general idea. So the big idea is that we can end up writing out that u sub k, which gives you the kth Fibonacci number, could be expressed as being equal to this vector 1, 1, 1, 0 to the kth power multiplied by u0. This is kind of like the base scenario where you have 0, 1. So this is the same thing as being equal to 1, 1, 1, 0 to the kth power, and then u naught is equal to 1, 0. And so what I'm getting at is you can find any Fibonacci number by just finding powers of this matrix, right? And so if you find the powers of this, so if you wanted to find the powers of this matrix, what you would want to do is you would diagonalize it. Like you would find the eigenvalues and the eigenvectors. And so what ends up happening is this matrix, if I let A be equal to 1, 1, 1, 0, it's going to end up having the following eigenvalues. The eigenvalues are going to be lambda 1, which is 1 plus the square root of 5 over 2. And then you're going to have lambda 2 is equal to 1 minus the square root of 5 over 2. And then so these are the two eigenvalues you end up getting for this matrix A. And then the accompanying or corresponding eigenvectors are going to end up being V1, where the first component of V1 is given by lambda 1. So it's this number right here. And then you have 1 down here. And then you get V2 is going to be the same thing, except it's lambda 2, 1 like so. And so with this information, you're able to pretty easily determine what the power of A is going to end up being. So what you end up finding is that you get this 1, 1, 1, 0, K ends up being equal to the vector or the matrix formed by these eigenvectors. So this is going to be lambda 1, lambda 2, 1, 1, multiplied by the diagonal matrix where the entries are given by your two eigenvalues. So it's going to be lambda 1, 0, 0, lambda 2 to the kth power. And then you find the inverse. So this is, just to make it clear, this is our x, this is our lambda, and then this is our x inverse. So you can find x inverse pretty quickly by using the determinant formula we derived before. This ends up being 1 minus lambda 2, and then minus 1, and then you have lambda 1. And then you have to multiply by 1 over lambda 1 minus lambda 2, where this lambda 1 minus lambda 2, or like this term here, is just the determinant of this matrix. And so if you go through with this, what ends up happening is that you end up getting that the second component, I know I'm kind of like glossing through this really quickly, like skipping over the computations, but this gives you the power of this matrix here. And so if you want to find like any Fibonacci sequence or any Fibonacci number, say like FK or something like that. So like the kth Fibonacci number, I didn't want to spend that much time on this, so I'm going to kind of skip through this as quickly as possible. This kth Fibonacci number is given by the second component of the following. So it ends up being 1 over lambda 1 minus lambda 2 I'm gonna be lazy and just copy and paste this because I didn't plan on talking about this for so long. I was planning on stopping at here, and then I just kept going pretty much. But then you would multiply by 1, 0, and this ends up being equal to what it ends up being equal to is it ends up being lambda 1 to the kth power minus lambda 2 to the kth power, and then you divide by lambda 1 minus lambda 2. Right, so this gives you a formula for finding the kth Fibonacci number. Again, it's much easier to plug in this into a formula than it would to like recursively go through and check what the kth Fibonacci number is via this process here. So like this is a lot easier, even though the numbers are a little bit annoying. For the computer, it's not as big of a deal as it is for us. Right, so this is kind of an application. We'll look at plenty of other applications, but I wanted to illustrate how, like, looking at powers of matrices can help you determine how to solve recurrence relations that extend beyond Fibonacci numbers in the future. Yeah, question.
Would it be safe to assume we're not going to see this on an exam?
Yeah, definitely. Yeah, this is it's pretty long. I mean, this process of like finding the eigenvalue, like especially the eigenvectors, actually takes a decent amount of time. Just because like the numbers here, like mostly we've been working with nice numbers, not like, you know, square terms or anything like that. So it's actually kind of annoying to find the eigenvectors here. So you don't have to do stuff like this or a problem like this on the exam. It's something we're going to talk more about probably in chapter 7 or so, like when we do like Markov chains. Any other questions about this? Yeah, so it's kind of a preview of how, I guess, powers can give you a notion of change, I suppose. Okay, so the last thing we'll look at is going to be the symmetric matrices. I feel like we're probably not going to have, I'm not going to make any promises. I was going to say, I'm probably not going to have enough time to say anything significant about symmetric matrices to the point where a question about them could show up on the exam, but I feel like we'll see how much we get through though. And maybe I'll change my mind. So symmetric matrices, these are a really nice class of matrices. Again, a matrix is symmetric. This is something you should know. But just as a reminder, a symmetric matrix is one of the form where you have A transpose is equal to A, right? So that's the nice thing about symmetric matrices. We'll make use of this property a couple of times. And so we're going to be able to make a number of nice conclusions about symmetric matrices that have real entries. And so we've seen before that any n by n matrix with n linearly independent eigenvectors is going to be diagonalizable. So like we have this following the equation here. And turns out that these symmetric matrices, or it turns out that every symmetric matrix is diagonalizable, and that these symmetric matrices also are going to have nice additional structure as well. So this proposition doesn't prove everything that I just stated. We're going to do a number of different proofs until eventually we get to the spectral theorem down here, which tells you that every symmetric matrix has the following factorization with real eigenvalues. And then what's particularly nice is eventually we'll be able to say that you have orthonormal eigenvectors. This is effectively saying you have an orthonormal basis given by the eigenvectors, which is a very nice context to be working under. So this is kind of what we'll be working to. The first thing we're going to prove in that vein is that if we have a symmetric matrix with real entries and we have eigenvectors given by v1 and v2, then as long as we can say that lambda 1 and lambda 2 are different from one another, what's going to end up happening is that v1 and v2 are going to be orthogonal to one another. So what this is saying is that if you have a symmetric matrix with distinct eigenvalues, then your eigenvectors are going to be orthogonal. And maybe you've been seeing on the homework that orthogonality between vectors is a stronger condition than just having linear independence. If two vectors are going to be orthogonal, it automatically means they're going to be independent to one another. So it's a stronger condition. And so these eigenvectors, as long as they have different eigenvalues, are going to give you an orthogonal basis. And so the proof of this is maybe a little bit unintuitive. So I guess how I'm going to start is I'm just going to be thinking about this dot product. Again, when you have the V transpose times V, or the transpose times something else, this is really just saying you're taking the dot product. And this is really going to, like, maybe it's like, why are we writing the dot product in this way? It'll be illustrated a lot better in this section because we're going to be thinking a lot in terms of the transpose because we're looking at symmetric matrices. And so the first thing I'm going to start off with is I'm going to look at V1 transpose times V2. This is the dot product of the two vectors. And we want to do things involving lambda 1 and lambda 2. So I'm just going to multiply this thing by lambda 1. Again, it's kind of like, maybe it's a little bit unintuitive where this is coming from. I'm just kind of like taking all the things we care about and putting them together into an equation. And so I'm going to move the parentheses around to shift focus around these two terms instead. So I can rewrite this as being lambda times V1 transpose times V2. And then, I mean, lambda is just a number, so it's not affected by the transpose at all. V1 is a vector, so it is affected by the transpose. So we can rewrite this in the following way. This is the same thing as doing lambda times V1 transpose times V2. Again, this is legal because lambda is not a matrix or a vector, so it's not affected by the transpose. So this is really just a different way of writing V1 transpose. So the reason why I'm writing it in this way is we're assuming that S has an eigenvector given by V1 with eigenvalue lambda 1. So we have lambda times V1 here. So you can use the definition of eigenvalues and eigenvectors to rewrite this in terms of S instead. So this is the same thing using the definition of eigenvalues and eigenvectors as having S times V1 transpose times V2. Right, so again, this is just the definition of eigenvalues and eigenvectors. It's the same thing as S times V1 from the assumptions we were making in the beginning. And so now when we distribute the transpose, it's going to look a little bit different. So now you can use this thing where if you do the transpose applied to matrix multiplication, you switch the order and you apply to each term individually. So this is the same thing as doing V1 transposed times S transposed times V2. And I know I just wrote it, but I'm actually going to erase this because it gets in the way. And so we're making the assumption that S is a symmetric matrix. So we have S transpose, that's just going to be equal to S over again. And so this is equal to V1 transposed times S times V2. And so this whole time, like we've just been thinking in terms of lambda 1, but we also have this lambda 2 that's involved as well. And so we want to get lambda 2 somewhere, and where we can get lambda 2 is this part right here. So I'm going to draw particular emphasis to this parentheses here. We have S times V2, where V2 is an eigenvector of S with eigenvalue lambda 2, which means that you can rewrite this as being V1 transposed times lambda 2 times V2. And so where am I going with this? I feel like it feels like we're just going in circles almost. But the main thing is if I move this lambda 2 to the outside, and then we take a step back and look at everything, we have lambda 2. So this is equal to lambda 2, and then this is going to be V1 transpose times V2. Right, and so what have we done? We started here, lambda 1 times V1 transposed times V2, and we ended with lambda 2 times these two things, right? So if I were to do the difference or look at the subtraction of these two terms, it should be equal to 0. Actually, let me kind of condense this equality. So like what we've shown, just taking the last term and setting it equal, or the first term and looking at the last term, this is condensing the equality. We get lambda 1 is V1 transpose times V2. This is equal. So we showed this is equal to lambda 2 times V1 transpose times V2. And so if I subtract, say, this term from this term, it's going to end up being equal to 0. So we can say something like lambda 1 times V1 transpose times V2 minus lambda 2 V1 transpose times V2 is equal to 0. And so we have that we can factor out. So this is just a number, right? This is a dot product between two vectors. So this is something that you can factor out. And if you factor this out, you end up getting that this is going to be V1 transposed times V2, and then multiplied by lambda 1 minus lambda 2. This is still equal to 0. And then the last assumption we made was that we were assuming that lambda 1 and lambda 2 is not equal. They're not equal to one another. So we can say definitively that this is not equal to 0 because lambda 1 and lambda 2 are not equal. And so that must mean that this is going to be equal to 0. And so this forces V1 transpose times V2 to be equal to 0, which then implies that you have V1 and V2 are going to be orthogonal to one another. So this one's a little unintuitive, like starting here and then we're just doing a bunch of weird operations until eventually we were able to kind of get to the same thing over again, except you have a lambda 2 in front instead. But the purpose is so that way we can subtract the 2, and then eventually we'll be forced to say that V1 is orthogonal to V2. Okay. Any questions about this proof at all? Yeah, so again, the main takeaway, if you wanted to summarize this in a single line, is that if S is symmetric, then distinct eigenvalues means that you have orthogonal eigenvectors. Right, so as long as you have different eigenvalues, you get different eigenvectors, or you get orthogonal eigenvectors, which is stronger than linear independence. So there's a couple of remarks that we can make based on this proposition. So these are pretty important. So it's kind of, some of it's going to be saying the same thing over again, but this implies, so what we just proved implies that a symmetric n by n matrix with n distinct eigenvalues has orthogonal eigenvectors. That's what I just said before. And so if the eigenvalues are distinct from one another, via normalization, the eigenvectors can be chosen to be orthonormal. So once you have the eigenvectors corresponding to these distinct eigenvalues, they're going to be orthogonal. So if you want an orthonormal basis, you just divide by the magnitudes of each of the vectors, and that'll give you an orthonormal basis. And so in other words, what ends up happening is that if you have a symmetric matrix with distinct eigenvalues, it immediately means it's going to be diagonalizable. Again, the main condition we care about for diagonalizability is independent eigenvectors. And we've just shown that if you have distinct eigenvalues, you get independent vectors. So these are really nice properties that apply to symmetric matrices, just from this one proposition. And so this next example, I guess, is like an illustration of these ideas. And so for this one, it wants you to show that the eigenvectors of this matrix S can be chosen to be orthonormal. And so the main characteristic that we care about with respect to S is that it's a symmetric matrix. And so from what we've just proven, if we want to show that the eigenvectors can be chosen to be orthonormal, really all we need to do is to show that the eigenvalues are different from one another. So it restricts the number of calculations that you need to do in order to guarantee that you have a really nice structure here. And so from the previous proposition, one second. So from the previous proposition, it suffices to show that S has distinct eigenvectors or distinct eigenvalues. So in this scenario, as long as you can show that the lambda 1 is not equal to lambda 2, that immediately determines that you have an orthonormal basis given by the eigenvectors, which is a very nice quality to have. And so we just compute the eigenvalues, and if we show they're different, we're done, right? So we just take the determinant. So finding the eigenvalues, you do the determinant of S minus lambda I. Right, so you just take S and you just subtract the diagonal by lambda. So this will be 2 minus lambda, 1, 1, and then 2 minus lambda again. And you compute the determinant. This is going to end up being equal to 2 minus lambda squared minus 1. And then if you FOIL this thing out and combine like terms, this ends up being equal to lambda squared minus 4 lambda plus 3. And then you want to set this equal to 0 and find what the roots are going to be. So you can factor this out by using the fact that like -1 times -3 is equal to 3. And if you add them, you get -4. So this ends up being equal to lambda -1 and then lambda -3. You set this equal to 0 and you find that lambda 1 is equal to 1, lambda 2 is equal to 3, or whatever order you want to write it in. And so the main point is because we have that lambda 1 is not equal to lambda 2, what this immediately implies is that we have orthonormal eigenvectors. Well, it means we have orthogonal, but then you just divide by the magnitude. Yeah, one second. So then we have, this implies that we have orthonormal eigenvectors. And then you can find those eigenvectors, but at the very least, we already know that S is now going to be similar to a diagonal matrix. So there's a lot more we can get from doing a lot less computations in this context. Questions? Do you have a question? Or?
So in factored form, if we have like lambda -1 like, to the power of 3, does that have a way of 3 different eigenvectors with 1?
Oh, and it's actually going to be a little bit more complicated than that. I mean, it could mean that, but there's going to be it's something we're going to talk about in chapter 7. Like there's like a whole theory that's dedicated to this. Like all the examples we've been looking at, like they have been having distinct eigenvectors, but yeah, there's like not always is what I would say. It's going to be, it's a little bit more complicated than that. And it's something we'll talk about later on, but it's a good question. It's going to depend on a number of different things. Any other questions about this example? Okay, so maybe the last example I'll do today is, let's see. I think I'll just do this example and then motivate whatever this next proposition. I feel like I can't really motivate this next proposition without going through this example because, well, if you look at this proposition, it's saying that if S is a real symmetric n by n matrix, then S has only real eigenvalues. Like all the examples we've been looking at have been like with real eigenvalues. So I want to do this example above to illustrate that you can have, so this is a non-symmetric matrix, so the proposition doesn't apply to this particular matrix, but you can have like a fairly innocuous looking matrix here. But if you find the eigenvalues and eigenvectors, what you're going to find is that they're going to have complex values, which makes things a little bit more difficult. But I do also want to observe other qualities that this has. So for this one, it wants you to investigate the eigenvalues and eigenvectors. And I kind of spoiled it in saying that you're going to end up having complex values. But there's a certain relation that also exists between the eigenvalues and eigenvectors that we want to find. So if I wanted to find the eigenvalues and eigenvectors here, again, you'll take this matrix and then you do A minus lambda I, find the determinant, and then you want to set it equal to 0, like we've been doing plenty of times so far. So this is going to be 1 minus lambda, 1 minus 1, 1 minus lambda. And if you compute the determinant, eventually you'll be able to write it as a quadratic polynomial with variable lambda. And it's going to end up being equal to lambda squared minus 2 lambda plus 2. And so if I set this equal to 0, you can use the quadratic formula to determine what lambda is going to end up being. So via the quadratic formula, you end up getting that lambda is equal to 2 plus or minus the square root of 4 minus 4 times 1 times 2 over 2. And what this ends up being equal to is that it ends up being equal to 1 plus or minus I. So you end up getting a negative number within the square root. So it introduces this I term, which is a little bit difficult to work with. We haven't really been working with complex numbers in this class. And as time goes on, we might dedicate, there's like a lot of different theory involving complex numbers that we might dedicate some time to later in the semester. But yeah, so this is like the first time we've been looking at like these complex eigenvalues. And so despite the fact that it's complex, we can still find the eigenvectors. Right, so we have lambda 1 was equal to 1 plus I. We had lambda 2 was equal to 1 minus I. And this one actually is fairly well behaved, I suppose. Sometimes finding the eigenvectors from complex eigenvalues can be incredibly annoying. But if you plug in lambda is equal to I plus 1, you end up getting the following. You get minus I, 1, minus 1, minus I. And so what you can do is you can multiply this first row by I, and then you can add it to this row, and it would end up canceling out what we have here. And then you can do some other manipulations. So I'm going to skip ahead a little bit and just say that you end up reducing to 1 I and then 0, 0. It's like one way of potentially writing this out. So you can cancel this row and then you can multiply this by I and you would get the following here. And so what this ends up implying is that we end up getting that V1 can be expressed as 1 I, which you can then express as the sum. So usually when you're given a complex number, you want to be able to decompose it as a sum of like something real and something imaginary. So you can write this as 1, 0 plus I and then 0, 1. And again, if you don't, I'm kind of skipping over this a little bit, but what I would say is like ignore, I'm just kind of giving a slight justification as to why this ends up being the eigenvector. It's not really the focus. Like what the takeaway from this is going to be is we can get complex eigenvalues and complex eigenvectors. And then the other observation is that if we have I, 1, minus 1I, so this is what you get when you plug in I minus 1 in for lambda here. And then if you row reduce, you can eventually write this out as being 1, and then you have minus I, and then you have 0, 0, which eventually gives you an eigenvector of the form 1, 0, or sorry, skipped ahead a little bit. This is 1 minus I, which you can write as being 1, 0, and then minus I, and then 0, 1. And so I'm asking, like, what do you notice here? Does anyone see what's going on between like the eigenvalues and the eigenvectors, or at least like a relation that exists between the two eigenvalues we have and the two eigenvectors we have? Like, how do they relate to one another? Maybe it's a long time since you've seen or heard this term before, but yeah, so the word I'm looking for, I don't have that much time, so I'll just tell you, is that the eigenvalues are complex conjugates of one another, as are the eigenvectors, right? So like the only difference between this eigenvector and this eigenvector is this is plus and this is minus. So like if you have these complex eigenvalues, they're going to be complex conjugates of one another, and their corresponding eigenvectors are going to be complex conjugates as well. And so what we end up finding is that the eigenvectors and eigenvalues are complex conjugates. So this is something we'll talk about more later on. Right now, I'm not too concerned about, like, I'm not going to ask you to do things with complex eigenvalues or eigenvectors on the exam. The reason why I wanted to go through this example is to say, like, for non-symmetric matrices, sometimes you get complex eigenvectors and eigenvalues, which is annoying. But this next proposition will prove, like a week and a half from now, is that if you have S is real and symmetric, then S only has real eigenvalues. So the eigenvalues and eigenvectors behave a little bit better. Okay, yeah, so we'll stop there. I guess later on today, I'll email you or send out an announcement with the exam review. So you'll have that by the end of today. And then the homework's due next Tuesday. So I pushed that back if you haven't seen that yet.